Hey everybody, it's Wednesday, September 30th. The last day of September has arrived. And for today, we are really going to get into talking about motion graphs. Now, at the end of the video yesterday, we started talking a little bit about motion graphs and how we can use them to describe the motion of objects. And so today, we're going to get into that in a little more detail. So yesterday when we were discussing graphs, we really only discussed position versus time graphs and talked about how we can interpret a position versus time graph to talk about the motion of an object. And so today, we're really going to get into that in a lot more detail by thinking about all of the kinds of graphs that you could see in this course. So the first thing that we should say under the heading graphical analysis is that to analyze motion graphs, we use two mathematical techniques. And those techniques, as I'm sure you may remember from honors physics, are slope and area under the curve. And so if we want to perform a calculation when there is a graph involved, these are the two math techniques we are going to use. Those of you who were in my honors class may remember this, but those of you who are not, rather than saying and writing, really writing more so though, area under the curve over and over and over again, I will abbreviate this as AUC. So when you are writing explanations like on homeworks or whatever, rather than writing out the area under the curve is, you could just write the AUC for our purposes. Okay. So it's very important for everybody to realize that our job when we are looking at graphs is going to be determining what the physical significance of the slope and the area under the curve are. And the physical significance of the slope and the area under the curve depends on which quantities are being graphed, right? So depending on the graph, the slope and the area under the curve will mean different things. And so I want to take a couple minutes to go through all of the graphs so we can talk about the meaning of the slope and the area under the curve. But obviously, first, before we do that, we have to answer the question, well, how do we determine the physical significance of the slope and the area under the curve in general? And the answer really all comes down to the equation. To determine the physical significance of the slope, you divide the y-axis units by the x-axis units. Now, why did I just say that it all really comes down to the equation? Well, if you look at the equation for the slope is the quotient of the y-axis change and the x-axis change, or the change in the y-axis variable over the change in the x-axis variable. And so the units then are going to be found by taking those quantities and dividing their units. So to find the physical significance of the slope, you divide the y-axis units by the x-axis units because that's what the equation says. Conversely, for area under the curve, to determine the physical significance of the area under the curve, you multiply the y-axis units by the x-axis units. And why would you do that? Well, think about all the area formulas you know. They all have one thing in common. I can think of a few here. The area of a triangle is 1/2 base times height. The area of a rectangle is length times width. The area of a circle is pi r squared. The area of a trapezoid is the average of the bases, 1/2 b1 plus b2 times the height. So all of these equations, they all involve multiplication. And as we were getting to yesterday, when we were talking about the kinematic equations, if an equation tells you you get the acceleration by finding the change in velocity over time, it is always going to be the case that if an equation tells you to divide two things to find the quantity, then really the equation is also telling you to find the units for that quantity You just divide the units of the terms in the equation. So since the slope formula involves division of the y-axis and x-axis units, we divide the y-axis and x-axis units to find the significance of the slope. And since the area formulas, which obviously, I hope this is clear to everybody, but if it's not, the area on a graph is never going to be a circle. And so these other three equations are going to come into play, and looking at them, all of those equations clearly say you take the base, or the width, and you multiply it by the length, or the height, or however you look at it. So since you're multiplying things in all the area equations, you multiply the units to find the units for the area under the curve. Now, before we get into the particular graphs, I just want to give this one note here. This will come back into play once we actually do one of these problems for real. And so I will mention this explicitly, but it's super important to note. This is very, very, very important. The area under the curve is always defined as the area between the x-axis and the line on the graph. And that is always true. Super crucial for you to write this down. The area under the curve is always defined as the area between two things, the x-axis and the line on the graph. So when we are doing problems, it's always important to keep that in mind. Okay, let's take a look at the individual graphs. So here we have a position versus time graph. This was the graph that we were looking at yesterday. And so if we take a look at this graph, most of the time they are labeled like this. Other times they are labeled with the units. So before you forge ahead on any of these graphs, I think it's very important that you make sure you are being careful about what the unit is for each variable on the graph. And so because position is measured in meters and time is measured in seconds, we'll just go ahead and label those there. So as we said here, the slope is equal to the change in y over the change in x. And in this case, the y-axis variable is measured in units of meters. The x-axis variable is measured in units of seconds. So we can say here the slope has units of meters per second. And we'll say here that that means it represents, so since the slope has units of meters per second, it represents velocity. Now, of course here, and there's a note about this at the end of the slides. I'll get to it probably in 4 or 5 minutes. The reason why we're saying velocity and not speed is for one reason and one reason only. And that's because position is a vector. And so it's important to remember here that vectors go with vectors and scalars go with scalars. And so because position is a vector, the slope must also represent a vector. And so in this case, it is velocity. Of course, and this note addresses it, so you don't have to worry about it for now. But if the graph was a graph of distance versus time, because distance is a scalar, that means the slope would have to represent a scalar as well. And so the slope still has the same units clearly, because distance has the same unit as position. But then in that case, the slope would represent speed, because the quantity being graphed, the distance, is a scalar. Okay. Now I'm going to erase this here in a second, but I just want to show it for a brief moment. As we said a moment ago, the area under the curve is defined as the area between the x-axis and the line on the graph. And so that means the area under the curve is in this red shaded region. I hope everybody looking at that can realize, just from the look of it, that that's a triangle. And so we'll just go ahead and think about this in terms of the area of a triangle. So the area of a triangle is given by the equation 1/2 base times height. And I hope it's clear to everybody that 1/2 is a number. It has no units. So all we're really concerned about are the units for the base and the unit for the height. And so the base of this triangle over here has units of seconds. And the height of this triangle over here has units of meters. And so the slope the area under the curve, or I'm going to write the AUC, has units of meter seconds. Now all you have to do is think. What quantity in physics has units of meter seconds? And the answer is nothing. And so we'll say here that the area under the curve has units of meter seconds, which means the area under the curve has no physical significance. So this is one of the rare instances where the area under the curve, because of its units, has no physical significance. So it really isn't that complicated. You know the units for position, velocity, and acceleration. And so if the slope or area under the curve has those units, then it means one of those things. And if it doesn't, it doesn't. And so in this case, the area under the curve has no physical significance. And that's it for position versus time graphs. Let's go ahead and take a look at velocity versus time graphs. Again, if the graph does not show the units, you want to go ahead and just label the units here. And so the units for velocity are meters per second, and the unit for time, of course, is seconds. And slope has a significance, which is determined by taking the x-axis units and the y-axis units and dividing them. And so the y-axis variable has units of meters per second. The x-axis variable has units of seconds. And so the units of the slope for a velocity versus time graph, meters per second squared. And so we'll say here the slope has units of meters per second squared, which means the slope represents velocity. Jeez Louise. Of course, that represents acceleration. So since the slope has units which are the units of acceleration, then that tells us the slope represents acceleration. Now, since acceleration has no scalar counterpart here, the slope just represents the acceleration. If it was a speed versus time graph, the slope would represent the magnitude of the acceleration. Okay. Now for the area under the curve, same thing here. Notice if we draw this dotted line, the area under the curve there is clearly a triangle. And so we'll use the formula for the triangle over the course of this discussion. And so the formula for the area of a triangle says the area of a triangle is 1/2 base times height. 1/2 is just a number. It has no unit. So the base of that triangle, that would be over here, has units of seconds. And the height of the triangle has units of meters per second. And since we can write this seconds as seconds over 1, that means the seconds cancel. And that gives us units of meters. And so we can say here, the area under the curve has units of meters, which means the area under the curve represents displacement. Now, of course, if you're wondering why is the area under the curve displacement and not distance, of course, this goes back to the idea that we were discussing before, that scalars go with scalars and vectors go with vectors. And so because this is a velocity versus time graph, which is a vector, the area under the curve must also represent a vector, which is displacement. If the graph was a graph of speed versus time, then the area under the curve would represent distance. Okay, moving on. Now we've got the position versus time graph, the velocity versus time graph, and so the last one for us to do is the acceleration versus time graph. Of course, as we mentioned, if the graph doesn't have the units labeled, we might as well go and label them. So acceleration is measured in units of meters per second squared. The time, of course, is measured in seconds. So one more time, the slope says delta y over delta x. So we take the y-axis units, we divide them by the x-axis units. That would give us meters per second squared divided by seconds, which, flipping and multiplying, just in case you don't see it, means we take meters per second and multiply by the reciprocal, so that would be 1 over seconds, and that gives us meters per second cubed, which we can interpret as a meter per second squared per second. This quantity is actually a thing in physics. You can look it up. The slope, which has units of meters per second cubed, represents jerk, which will always be 0 in this class. And the reason why it will be 0 is because we always said here in this class that the accelerations that we'll be dealing with are constant. So I'll just squeeze that in down here. That's because we'll always be dealing with constant accelerations. Now, this is the part of the year, or at least the part of the lesson, that usually disappoints me a little bit. Because whenever I show this in class, usually somebody raises their hand and says, well, what does jerk actually mean, though? You should be able to figure this out based on what we said over here. Remember, you can always break units down to interpret them. First of all, if this is an acceleration versus time graph, then the slope shows you the rate of change. So jerk shows you the rate of change of acceleration. If you want to know exactly what that means, it tells you how much the acceleration changes by each second. So if the jerk was 1 meter per second cubed, that would tell you the acceleration is changing by 1 meter per second squared per second. But of course, because we said, and I believe I said this like a couple times yesterday, because we're only dealing with constant accelerations in this course, the jerk will always be 0. You're never going to see an acceleration graph that looks like that. At least for the AP test material, it'll always look like this, because the slope is going to be 0. Okay. Now, clearly, the area under the curve, this is the exact same graph, so it's a triangle. So we have 1/2 base times height. Obviously, as we've said now 2 times, now this is the third. Half is just a number, so it has no units. The base of that triangle is seconds. The height of that triangle is meters per second squared. So one of the seconds cancels, and we end up with meters per second. And this is the time of the period where I try to make sure that everybody has this down. So I say, all right, guys, that's the unit. What does the area under the curve for an acceleration versus time graph represent? Somebody raises their hand and says, the speed. And I say no. And then somebody thinks they've realized what that person said wrong. Acceleration, remember, is a vector, so somebody else raises their hand and says it represents the velocity. The answer to that, again, is no. This one's a little bit tricky, but it's an important lesson for the year. We'll say here the slope, which has units of meters per second, represents the change in the object's velocity. Now, of course, the big question is, well, how are we supposed to know that the slope represents the change in velocity and not just the velocity itself? Well, sometimes it comes down to looking at the equation. It's important to realize here that what we did was we took the x-axis variable, time, and we multiplied it by the y-axis variable, acceleration. And when you take the equation for acceleration and you multiply acceleration times time, that's not equal to the velocity, but it's equal to the change in velocity. And so sometimes, while the units are always a good guide in terms of determining the physical significance of the slope or area under the curve, sometimes you just need to look at the equation for the variables too. That's very important, so let's go ahead and write that down. All right, so let's take a few quick notes here. First note, while the units are a great guide for determining the physical significance of the slope or area under the curve, sometimes it's instructive to also look at the equation which relates those variables to determine its true physical significance. You will be seeing this very shortly when we do an experiment on accelerated motion. This is very important to remember this. It's good to look at the equation and look at the units. That's going to particularly come into play when we look at graphs that are a little more complicated than just like your standard position versus time, velocity versus time, and acceleration versus time graphs. Take a second to pause this video and write that down, and when you hit play, we're going to write down one more very important note. Next note, pretty important. We already mentioned this. I just want to formally write this down because I did mention it. If we're talking about scalar versions of graphs, it's important to realize while we discussed the vector version of these graphs, for the scalar versions of these graphs, the slopes and areas under the curve represent the scalar version of those quantities. So scalars go with scalars and vectors go with vectors. Now that note is written a little ambiguously because to write it very specifically would require a lot of words. But the basic idea is position is a vector. So the position versus time graph slope is velocity. If we have the scalar version of that graph, which is a graph of distance versus time, then the slope is the scalar version of velocity, which is speed. If we're talking about a velocity versus time graph, which is a vector, the slope represents the acceleration and the area under the curve represents the displacement. So if we have a graph of speed versus time, because speed is a scalar, the slope represents the magnitude of acceleration, whereas the area under the curve represents the distance, because speed is a scalar. And for acceleration, it's not a great analogy, but the area under the curve, instead of representing the change in velocity, would just represent the change in speed if all that was graphed was the magnitude of the acceleration instead of the acceleration itself. That's the idea. All right, now let's go ahead and see how all of this can be applied to a problem in terms of just pure calculation, and then I'm going to give you a bunch of fun ones to solve and think about on your own. So the first thing that we should do is read the question, of course, and it says, using the velocity versus time graph shown above, calculate 1, the acceleration experienced by the object from t equals 0 seconds to t equals 10 seconds, and 2, calculate the displacement experienced, it's supposed to be past tense, experienced by the object over the whole 15-second time interval. So let's take a look at the graph in more detail. They want us to calculate the acceleration experienced by the object over the whole time interval. And so what I want to do here is show you specifically how I want you to do these calculations. And so the first thing that we should say here is, since the acceleration is determined by finding the slope, we're going to show this just like a straight up slope calculation. Remember, straight up slope calculations are performed by finding 2 points on the graph. So my 2 points on the graph are going to be this point and this point. You don't have to always take it at the end, but I think that these 2 points are very easy to see the coordinates of, like, right away. And I've captured the whole time interval too, which obviously doesn't hurt. So my first point, remember, when you're writing down points, you always write x comma y is 0 seconds, comma 10 meters per second. And the x-axis variable here, because it starts from 0, is just 0. And the second point, notice now the x-axis variable is 10 seconds, but because this line ends up extending below the x-axis, the y-axis variable, or the y-axis coordinate, is negative 10 meters per second. So we have 10 seconds, negative 10 meters per second. And we are looking for the slope, which is equal to the acceleration, which is our unknown. It's very important to equate these two at some point in the work, at least once. And so you might as well just do it here in the beginning, so you're making it explicitly clear to anybody who's looking at your work that you know and understand that the slope is equal to the acceleration. I'm going to do it every time just because that's how I do it. But it's important to realize you only need to write m, the symbol for the slope, is equal to a, the symbol for the acceleration, once. And so the slope formula, remember, is y2 minus y1 over x2 minus x1. And so here we just have to plug it in. Pretty simple. So our y2 is negative 10 meters per second. Y1 is 10 meters per second. And x2 is 10 seconds, whereas x1 is 0 seconds. And that's it. So negative 10 minus 10 is negative 20 meters per second. And negative 20 meters per second over 10 seconds is negative 2 meters per second squared. And that's it. The main thing to remember is that when you're showing these slope calculations, you just treat it like it's a regular old slope problem from math. Now, I think it's just important to take a brief moment to talk about what that means. So clearly, from what we've talked about how to interpret information about an object's acceleration, that acceleration tells us the velocity of the object changes by negative 2 meters per second per second. But that doesn't always mean the object is slowing down. Looking at the graph, from 0 seconds to 5 seconds, because the initial velocity was positive, the object is in fact slowing down over those first 5 seconds. But after 5 seconds, because the initial velocity is 0 at 5, and then very shortly after 5 it's negative, the object begins speeding up in the negative direction. So it's important to realize for a velocity versus time graph, whenever you see something that looks like this, at the location where the object crosses the x-axis. Sorry, I just said the object crosses the x-axis. What I meant to say was the line crosses the x-axis. That's where the object turns around. And now from 5 seconds to 10 seconds, the object is speeding up in the negative direction. And of course, its velocity is changing by 2 meters per second. Of course, that's negative though, every second. So the velocity goes from 0 to negative 2 to negative 4 to negative 6 to negative 8, finally reaching negative 10 meters per second by 10 seconds. Okay. Now, the question asked, what is the displacement experienced by the object over the whole 15-second time interval? And now I think it would be important to take a moment to discuss the note that I put up before. Note that I put up before said the area under the curve is defined as the area between the line on the graph and the x-axis. So I think it's always good when you're doing these, at least first when you're getting the practice with them, is to sort of get a sense of what that area is going to look like. This part would be our first area. And then notice the x-axis extends over here, making this our second area, or second and third area, however you like to look at it. So you could break this up into this triangle and this rectangle, or you can just treat this as a trapezoid, however you like. I'm going to show the calculation treating it as a trapezoid because I'm sure a lot of you are fairly familiar with the triangle and rectangle version of this. And so let's go ahead and solve for that area. So the first shape, as we saw, was a triangle. And since we were calling that the first area, we'll label those variables B1 and H1 for base 1 and height 1. So the size of base 1 here, the base of this triangle, is 5 seconds, and the height of that triangle is 10 meters per second. So base 1 is 5 seconds, and height 1 is 10 meters per second. Now, since we said we're going to treat this as a trapezoid, the trapezoid has two bases, the bottom base and the top base. And because this has two bases, which I'm calling base 2 and base 3, but because this is only the second height, I'll just call it H2. You could call it H2-3 or 2/3. The only reason why I'm not going to do that is because I feel like that usually is more confusing, as kids over the years end up asking me, what does height 23 mean? So we'll call that height 2 because it's the second height. So let's just get that out of the way first. Notice the height of this trapezoid is -10 meters per second. And that part is very important that you make that height negative because that height is below the x-axis. Now, it doesn't really matter what you call base 2 and base 3, but I'm going to go ahead and I'm going to call this base 2 just because it's at the top here. And I'm going to call this base 3. So base 2 goes from 5 to 15 seconds, and so that will be 10 seconds. And base 3 goes from 10 to 15 seconds, so we'll call that 5 seconds. And we're looking for the total area, which is equal to the total displacement, which is our unknown. And so now we'll set it up. It's going to be a fairly long equation, but we'll be able to do it in one shot. The total area, which is equal to the displacement, is the area of triangle number 1, which is 1/2 base 1 height 1, plus the area of the trapezoid, which is 1/2 base 2 plus base 3 times the height H2. Now, a lot of people end up telling me that they can't remember the area for a trapezoid. I never remembered the area for a trapezoid when I first started teaching this class. I think the easiest way to remember this is that when you take base 2 and you add it to base 3, and then you divide that by 2, essentially what you're taking is an average, right? When you add two things and divide it by 2. So the way that I remember the area of a trapezoid formula is I just say it's the average of the bases times the height. And so now we just go ahead and plug our numbers in. We have the total area is equal to the total displacement, which is 1/2 of base 1, that's 5 seconds, times height 1, 10 meters per second, plus 1/2 B2, which is 10 seconds, plus base 3, which is 5 seconds, times height 2, which is -10 meters per second. Now, you could just show the answer on the next line and have that be it, but I'm just going to go ahead and show the intermediate steps because I don't want to take out a calculator to do the math. So 5 times 10 is 50, half of that is 25, right? And then we have here 5 plus 10 is 15. 15 times -10 is -150. And then half of -150 is -75 meters. And so that makes the total area, which is equal to our displacement, positive 25 plus -75, which gives us a final answer here of -50 meters. Now, whichever way you want to explain it, I think that answer makes a heck of a lot of sense. Because looking at the graph, we can clearly see that the object spent a much longer amount of time traveling at a negative velocity. And even just giving a brief, like, eyeball look at the graph here, we can see that the area above the x-axis, shown in yellow here, is much smaller than the area below the x-axis, shown in yellow down here. So because there's so much more negative area than positive area, it's pretty clear that the negative displacement after 5 seconds is bigger than the positive displacement it had experienced before 5 seconds. And so notice here that from 0 to 5 seconds, I'm going to put the pointer back on because that's hard to see. From 0 to 5 seconds, the displacement was positive. As soon as 5 seconds occurred, the object turned around and started moving back towards the origin. Notice all of that displacement that it experienced from 0 to 5 seconds was erased by t equals 10 seconds. These two areas have equal magnitudes, and so they cancel out. These two triangles are equal in area, so they cancel. And then the object continues traveling to the left, and so really its total displacement is just shown to you here by the area of the rectangle. And that's it. So every single time you show a slope calculation, I want you to show it like you would do in math for any ordinary slope. And anytime you show an area under the curve calculation, I want you to show it using the symbols for the area under the curve. I just want to take a very brief moment to address one point I made earlier. I think it's pretty easy to see here what area is larger, whether we're talking about the area above the x-axis or below the x-axis, but sometimes, especially on the AP test, you'll be asked to compare areas which look like they're the same size, but are actually not. And so a good little technique here to estimate how big the areas under the curve are without actually having to calculate it is to just count the number of boxes. If they label two segments of a graph, segment A and segment B, and you're not sure which one is larger, if you just count up the number of boxes in the grid space, that'll give you an idea, because each of those grid space boxes has a constant area. Take a second to write that down, and then we'll go ahead and look at some additional problems on some worksheets. And that brings us to the end of the stuff I want to show you for today. Now, usually what we do in class after we solve that problem is I give you a bunch of problems to work on your own. I think it's super crucial at this point in the year that everybody gets a really good intuitive feel for understanding graphs. And so I give you a bunch of problems to work on your own. Now, of course, because we are not meeting in person, I want you to go ahead and try these either on your own or while talking to somebody else from your class. But if you go back to the original post where this video was, you'll see a copy of a worksheet. That worksheet has the title, Graphical Representations of Motion, Position or Velocity Graphs, Direction Change. And there are two questions on this sheet. This one, B1 QRT 31, and then B1 QRT 34. Now, notice all of these have codes. The codes mean something. This code stands for like qualitative representation translation or something to that effect. This is a good kind of question to prepare us for the AP test, because one of the free response questions on the AP exam is usually referred to as a qualitative quantitative translation. And so basically taking the information shown to you in the graphs and being able to put it in words is going to be a very useful skill for the year. All right, so the first one we're going to work on here is B1 QRT31. And because A and B are very similar, I want you to go ahead and work on both of these at the same time. So the question says for part A, if the vertical axis of the graph is position, does the object ever change direction? If so, at what time or times does this change in direction occur? Explain your reasoning. And part B says if the vertical axis of the graph is velocity, does the object ever change direction? And if so, at what time or times does this change in direction occur? Explain your reasoning. So I want you to take, let's call it 5 minutes, and pause this video and work on these problems. Try to explain your reasoning, give an answer, and when you hit play, we'll go over these. Now, I want to be very clear about one thing before you do this, though. I think you may have noticed this video is a little shorter than some of the previous videos because I am assuming that you are actually building in this time, taking a few minutes to pause the video, look this question over, and then actually do some thinking about it on your own before you hit play and hear me discuss it. So I urge you to pause this video here, take, let's say, 5 minutes to answer A and B for this question, and when you hit play, we'll go over it. So in this question, they are asking in part A, if the vertical axis of the graph is position, does the object ever change direction? If so, at what time or times does this change in direction occur? So the answer here is no. The object does not change direction. Now, of course, the question is, how do you actually know that? Well, I think the first most important question for us to answer is, how can we determine the direction an object is going in general? And the answer here is pretty simple. The direction in which an object is traveling is determined by the sign of the velocity. We can say here, since this is a position versus time graph, and I'll just write x versus t, slope represents the velocity. Since the slope is always positive, the object is always traveling to the right. That's the idea here. So the object does not change direction. The direction in which an object is traveling is determined by the sign and the velocity only. Since this is a position versus time graph, the slope represents the velocity, so we can figure out the sign of the velocity just by looking at the sign of the slope. And since the slope is always positive, that tells us that the object is always traveling to the right. And that's the idea. Geez, sorry guys. Hopefully that one wasn't too bad for you to work out. Now part B, and I'll see if I can leave that there as I scroll down. Part B says if the vertical axis of the graph is velocity, does the object ever change direction? And so once again, we have to answer the question, how do we determine what direction an object is traveling in? And pretty clearly, I think, the answer is based on the sign of the velocity. And so if this is a velocity versus time graph, the velocity starts out negative down here and then ends up positive over here. And it changes direction there. So yes, the object changes direction at time t equals 4 seconds. The direction in which an object is traveling is determined by the sign of the velocity. Since the sign of the velocity can be determined by looking at the y-axis, we can see the velocity changes from being negative to being positive at t equals 4 seconds. And that's it. Now, what is the main takeaway here? The main takeaway here It's pretty straightforward. The direction in which an object is traveling can be determined by the sign of the velocity. So let's go ahead and write that down. Note, the direction in which an object travels can be determined by the sign of the object's velocity. That's a super crucial, important point for analyzing and interpreting graphs. Take a second to pause this video and write that down, and then we'll go ahead and we'll look at another problem. All right, let's go ahead and take a look at another one. If you look on this worksheet on the back or on the second page, you'll see another question, which has the code B1-QRT34. And it says velocity versus time graph direction. And it says a unicyclist, someone riding a single wheel cycle, is moving along a straight street oriented east-west. In drawing the graph, east was taken as the positive direction and west was taken as the negative direction, as is usually the case. And the questions here are asking about, at various times, is the cyclist moving or accelerating? I don't want you to do all these because they get repetitive to some degree. I want you to do A. I want you to do B. I want you to do C. And I want you to do E. So A, B, C, and E. And I want you to take 5 minutes, pause this video, and answer all of those questions. This is a velocity versus time graph. You're answering, at 1 second, is the cyclist moving? If so, in what direction? Explain your reasoning. At 1 second, is the cyclist accelerating? If so, in what direction? Explain your reasoning. At 9 seconds, is the cyclist moving? If so, in what direction? Explain your reasoning. And then E, at 4 seconds, is the cyclist moving? If so, in what direction? Explain your reasoning. Now, I want to be very clear before you pause this about this part of the course. Writing explanations is like the whole name of the game here in AP Physics. And so it's super crucial that while we are outside of the classroom, you actually take the time to do this. So I'd like you to pause this video here for 5 minutes, work on these answers, and when you hit play, we'll go over it. Okay, so hopefully you got a chance to think about these problems and wrote down an answer. Now we'll take a moment to review them. So part A was the first one I asked you to do. And part A said, at 1 second, is the cyclist moving? If so, in what direction? Explain your reasoning. So the first answer here should definitely be yes. The cyclist is, in fact, moving at 1 second. We know that because the velocity, which is shown by the y-axis variable, is not 0. So the main point here is just to answer the question and explain it. So the sign of the velocity shows the direction in which the object is moving. You see how often this comes up? So since the sign of the velocity shows the direction in which the object is moving, all we have to do is look at the sign of the velocity to see which direction the object is moving in. So we'll say here, since the object has a negative velocity at time t equals 1 second, and negative is defined as est, the object is moving west at t equals 1 second. And that's it. That one's pretty simple. So the cyclist is moving at 1 second. We can tell that because the velocity is not 0. And since the sign of the velocity shows the direction they're moving, since the velocity is negative and negative is west, they're moving west. Part B says, at 1 second, is the cyclist accelerating? And the cyclist is accelerating at 1 second. So we'll put this one over here. Now, the reason why I didn't have you answer D or F is because the cyclist is always accelerating. And we can tell that because we can determine the acceleration from a graph of velocity versus time and looking at the slope. So the first thing we'll say here for the answer is yes, the cyclist is accelerating. And we'll say here the cyclist is accelerating in the positive direction. Now, how are you supposed to explain that? Well, if you go back in the notes to something we said the other day, I want you to answer all graph questions by saying the slope represents blank, then say what the slope is doing, and then tell me what's happening to the thing the slope represents. So we'll answer this by saying, since the slope of a velocity versus time graph represents the acceleration, and the slope is constant and positive, the acceleration is constant and positive, which is defined as the eastern direction. The cyclist is accelerating to the east. And that's the idea behind that one. And I hope what everybody realizes is that because that slope is constant throughout this entire time interval, throughout the 10-second time interval shown here in the graph, the cyclist is always accelerating. And so it'd be the same answer for part D and the same answer for part F. So the cyclist is always accelerating because the slope represents acceleration, and since the slope is constant and positive, the acceleration is constant and positive. And since positive means east, they're accelerating in the positive direction. Okay. Now let's take a look at part C. Part C is asking about 9 seconds, so I'll scroll up here and show the graph at 9 seconds. This answer is going to be pretty similar to A. Yes, the cyclist is moving at 9 seconds, and we'll say at t equals 9 seconds, the cyclist is moving in the eastern direction. Oh boy. Since the sign of the velocity determines the direction in which the object moves, the fact that the cyclist has a positive velocity tells us the cyclist is moving east. So at 9 seconds, and I'm just going to scroll up for a second, I'll come back down to that explanation. In 9 seconds, the velocity is positive. Positive, as they told you in the directions, means east. So yes, at time t equals 9 seconds, the cyclist is moving in the eastern direction. Since the sign of the velocity determines the direction in which the object moves, the fact that the cyclist has a positive velocity tells us that the cyclist is moving east. And the last one I wanted you to do was E here. And if you look at E, E is asking you about time t equals 4 seconds there. And notice at time t equals 4 seconds, that's just when the object, or when the line representing the motion of the object crosses the x-axis. That means the velocity is 0. So no, cyclist is not moving at t equals 4 seconds. Since the velocity of the object is 0 at t equals 4 seconds, the object is not moving, or the cyclist is not moving. That one's pretty straightforward. It's important to realize when on a velocity versus time graph, the line is crossing the x-axis, that's when the velocity is 0, because that's when the cyclist is turning around. They were transitioning from a negative velocity, meaning moving to the west, toward having an eastern velocity, meaning moving in the positive direction. And so for a brief instant at 4 seconds, the cyclist isn't going to be moving. Now, F here, I didn't assign to you, but it says, is the cyclist accelerating? We already sort of answered that by talking about the answer to B, because the slope is constant the whole time. But I just want to go and write that in the notes real fast, because that often is a confusing point. A lot of people think that because at 4 seconds the cyclist stopped, that means they're not accelerating. But it's important to realize if the velocity is 0, that does not necessarily mean the acceleration is 0, because you have to ask yourself a simple question. If at 4 seconds the cyclist has no acceleration, then how the heck did they start moving in the positive direction? They have to be accelerating. So let's just go ahead and write in the notes very quickly at just because the velocity of an object is 0, the acceleration doesn't also have to be 0. Velocity and acceleration are independent. In that sense. Now, obviously, the acceleration causes the velocity to be what it is, but it's important to realize that at that instant, the acceleration is what made the velocity 0. And so what we can say here is when an object turns around, the acceleration causes velocity to be 0 for a brief instant before the object starts gaining velocity in the new direction, which incidentally is the direction of the acceleration. Take a second to pause this video and write that down. And when you hit play, I want to explain that last line specifically in the context of this problem before we move on. Okay, so looking at this last line one more time, it says when an object turns around, the acceleration causes the velocity to be 0 for a brief instant before the object starts gaining velocity in the new direction, which is the direction of the acceleration. So notice here in the beginning, the initial velocity is negative. So VI or V naught is negative. But the acceleration, if you look at the slope, is positive. And as we said yesterday, when the initial velocity and the acceleration are in opposite directions, the object slows down. And as you can see here, as we move along this line, the velocity gets closer and closer to 0 until it hits 0 at t equals 4 seconds. But because that acceleration is still acting to the right, and as you all know from honors physics, accelerations are caused by forces. So because the object is still being pushed on to the right, it's still accelerating to the right. And so now that it still has an acceleration acting to the right, it speeds up and speeds up more and more to the right. That's the idea here. You always want to put all these rules together. Initial velocity and acceleration are in the opposite direction. It's going to slow down until it stops. Then it speeds up in the direction of the acceleration. Right? Think about it. The velocity here is -2. So the velocity goes from -2 to -1 to 0, but then it goes from 1 to 2 to 3 to 4 and so on. That's the idea. And with that, that's it for today. Tomorrow, we are going to take a good look at some more confusing and counterintuitive problems like these, which will hopefully give you a more comfortable feel with the graphing motion problems. Have a good one, everybody.